In this video, we're going to have a look at what you need to learn before you start your A-level in physics to make the best possible start, the transition work. We're going to look at these 6 topics: vectors, algebra, logarithms, dimensional analysis, graphing skills, and errors and uncertainties. Now, it may well be that you've covered some of these before. For example, you might have studied vectors in mathematics and physics already for your GCSEs, or you might have studied algebra to some level. We should have studied those things. We should also have studied some graphing skills and errors, but it doesn't mean that you've covered them to the right sort of level to make a good start. Let's start by looking at vectors. So vectors really start off in your physics education as an inconvenience, an extra bolt-on activity that you could do without. You'll learn that there's distance and displacement. Displacement is distance with a direction, and you learn that you have speed and velocity is speed with a direction, and it feels like an extra. Well, actually they become very important in A-levels. We've got quantities that are vector quantities where if you don't handle them properly, you're going to get stuck. So we need to learn how to handle vectors properly. Well, a vector is just a quantity that has a direction and a magnitude, and we represent that graphically as an arrow, and the direction of the arrow is the direction of the vector. The length of the arrow is the magnitude of the vector. So here I've got vector A and I've got vector B, and you can see that A is a different length to vector B, and A is in a different direction to vector B. Fine. Now when we write down our vectors in an equation, there are a few different ways we can do it. We can either just use bold letters, which is the standard way of doing it in printed text, but you're not going to do that in handwriting. So one way is to do arrows over your vectors, one is little wiggly lines over your vectors, one is to underline your vectors. It's up to you. Whatever you find most convenient, that's what you should use. They're all perfectly good conventions. When adding two vectors, what do? Well, we either redraw the second vector on the end of the first vector, or we draw the first vector on the end of the second vector. So here I'm taking vector B and I'm drawing it on the end of vector A. Vector C is indicated with this magenta arrow here. So this is A plus B equals C, but as a vector sum. We could easily have also done vector A drawn on the end of vector B, and it would look like this. And you'll notice that C is the same whether we add B onto the end of A or A onto the end of B. That's a parallelogram, and very often students in GCSE level will learn about drawing a parallelogram of forces, for example, to add forces, and graphically adding things using a scale diagram. Okay, so bit of a summary, notations, those are what I've already mentioned. Graphically adding vectors requires the use of a protractor, use of a ruler, and very careful. It's quite a skill to do, but it is a GCSE skill. So let's move this on a step. We're going to add our vectors algebraically instead. To add two vectors algebraically, first of all we need to look at components of vectors, and we have to understand what perpendicular components are. We can then take the components of our two vectors that are parallel and add them together, and then we can do Pythagoras on those resultant components because they will be perpendicular to each other. That's quite a mouthful, so it's going to be easier to understand if we look at some examples. I've got a little note here saying you can use Pythagorean theorem to add perpendicular components. That's one of the last steps. And we can use the function arctan, which on your calculator might be listed as tan to the minus 1. This is the inverse function of the tangent function, and that will be able to be used to give you the direction of the resultant vector. So when we add vectors together, the most common way that we use vectors in A-level physics is called the Cartesian system, the Cartesian coordinate system. Or sometimes it's also called the rectangular coordinate system. Now this is not true in all cases. When you have a look at electric fields, gravitational fields, you'll be actually using a polar coordinate system, a spherical polar coordinate system. There's also a cylindrical polar coordinate system, in which vectors are described as a magnitude, a length, but then the direction is given in two different planes. Well, we won't be using that today. So what is the Cartesian coordinate system? Well, here's a three-dimensional shape, a cube. We can imagine that we can describe any position within this cube if we can say how far along each of its perpendicular lengths we are. So let's place this cube in the corner of a box and get rid of the cube. So there's the interior corner of a box. And we can describe those three perpendicular directions thus. We can give them letters. We could say this one that's red is X, this one that's green is Y, and this one that's blue is Z. It looks something like this. Now actually these directions could have been labelled in different ways. Instead of calling this one X, this one Y, and this one Z, we could have called this one X, this one Y, and this one Z. Or we could have called this one X, this one Y, and this one Z. But it doesn't matter which coordinate system you use, they all agree, all you're doing is rotating it around. They all agree with what's called a right-handed convention, which I'll talk about in a bit. So the angle between X and Y is 90 degrees, and the angle between Y and Z is also 90 degrees, and the angle between Z and X is also 90 degrees. So let's talk about that right-handed system then. In the right-handed system, what you do is you extend your fingers of your right hand in the direction of X, and then the direction you can turn your fingers, that's the direction Y. The thumb points in the direction Z. You've got to use your right hand. So taking my hand like this, X, then rotating round to Y, Z points up. That is a right-handed coordinate system. We could have put X, Y, and Z like this. So this one's sort of pointing towards you. X is here, so I push my fingers out in the direction of X, curl them up in the direction of Y. Well, Z has to be pointing out towards you, out of the screen. So that's our right-handed coordinate system. A left-handed coordinate system would be the same idea, except you use your left hand instead. We are going to use right-handed. So, unit vectors. Unit vectors are vectors along each of those cardinal directions, X, Y, and Z. But these unit vectors only have a magnitude 1, and they don't actually have any dimensionality. Now, what are dimensions? We'll talk about that later. So these unit vectors only have direction. That's it. In the direction X, we have the unit vector I. In the direction Y, we have the unit vector J. In the direction Z, we have the unit vector K. And we indicate their unit vectors by putting that little hat over the top, a circumflex symbol. That tells you that you have unit vectors. So a vector, S for example, written in bold because it's a vector, could be written as well, that A should be not bold then because it's not a vector, that's a magnitude. That's better. So A, that's the magnitude in the direction of the X direction. So that's multiplied by the unit vector I, plus B, that's the magnitude in the Y direction, multiplied by the unit vector J, and then add C, that's the magnitude of the component along the Z direction, and that's multiplied by the unit vector K. So that is how we can represent any three-dimensional vector. A, B, and C are scalars, that's why they're written without being bold, and therefore they are just the magnitudes, but they do also have the units of the vectors in there. In order to be able to add these three components together, they have to be dimensionally homogeneous. That means they have to have the same dimensions. And again, we'll talk about dimensions a little bit later. It doesn't need to be complicated, but we need to do it properly. So you don't have to draw the Cartesian coordinate system like this. Actually, this isn't always the convenient way to draw it. Instead of drawing the y-axis up and the z-axis towards us, we could actually draw it so that the y-axis is away from us and the z-axis is up. using our right-hand coordinate system. That still works. But what it does mean is that if you go in the positive direction of I, the positive direction of J, and the positive direction of K, you're going up towards the top right, which is much easier to visualize. So this is my preferred orientation of the axes. This is why I do it this way. Anything down here is negative in the X, Y, and Z direction. Anything up here is positive in the X, Y, Z direction. That's, I think, pretty straightforward. So our vector, any vector can be represented graphically. Here I've got A units of I in the X direction, B units of J in the Y direction, and C units of K in the Z direction. Fine. Well, let's suppose that I have a two-dimensional vector in the plane XY. Maybe it's drawn like that. Well, that's going to be, in this case, I've drawn it to scale, A, I across, and B, J up, and that gives you that. And then maybe we want a three-dimensional vector, so we're going to add CK to that. That gives you something that comes up there, where we've got CK drawn here. And so you can see I've now drawn the three vectors one after the other, AI plus BJ plus CK, exactly what we said before. You draw each vector on the end of the first. Now with three vectors, you could, well, the end of the previous one I should say, but we've got three vectors here, so we could have done this in all sorts of different orders, but you'd still end up with the same resultant vector S. I've got this coordinate thing on the right here just to remind you of what it looks like. So these are three perpendicular components of vector S. If we want to compute the direction of a vector, let's just take two-dimensional vectors, but if you can do this for 2 dimensions, you can do this for 3 dimensions. If we want to compute the direction, we use arctan. So the tan of an angle, the tangent of an angle, is going to be the opposite over the adjacent. In this case, it's A over B. So why have I written B over A there? That looks like another mistake. That's better. So the tan of our angle, the tangent of our angle theta, is going to be the opposite. That's A divided by the adjacent. That's B. So the arctan of A over B is going to be our angle theta. So we can use that to determine the direction of our vector. Okay, fine. So how do we add vectors? Well, we could do it graphically, or we could do it in these 5 steps. First of all, we pick our orientation of our coordinate system, make it something convenient. Then what we do is we determine our perpendicular components. And we could do this for both vectors, or we could take one of those vectors, we're adding 2 vectors together, so we could take one of those vectors as being parallel to one of those Cartesian coordinate directions, and then the magnitude in the other 2 would be 0. And that's going to make the sum a little bit easier. We add together components of the 2 vectors that happen to be parallel, and then we use Pythagorean theorem to compute magnitude, and finally step 6, we can calculate the angle. So here's an example. We have 2 vectors, A and B. A is 10 meters, B is 20 meters. The angle between those 2 vectors is 20 degrees. I want to add the 2 vectors together. What do I do? Well, okay, I need a bit of space for this. I might not have enough space on this screen, but we'll see how I get on. First of all, step 1, I'm choosing my coordinate system. Well, I haven't been told what direction A and B are, so I might as well just choose a sensible coordinate direction like this. I'm then going to draw my A and my B like this. So this is to scale. This is A, and then 20 degrees around from A is B. There's B. So that's fine. And if I was doing a scale diagram, what I would now do is redraw B on the end of A, get my ruler, decide my scale, but I'm not going to do that. What I'm going to do is just take one of these vectors. I'm just going to take B, because B is the one that has components in both the X and Y direction. A doesn't. A's component in the Y direction is 0. So that's easy. B has components in the X and Y direction. So this is B. In the X direction, I can say that's BX, and in the Y direction, I can say that's BY. and that's a right-angled triangle. So what's bx and by equal? Well, we could do some maths. In this case, b was 20 meters, so by is 20 meters multiplied by the sine of 20 degrees, and bx is 20 meters multiplied by the cosine of 20 degrees. And we do need to be able to do this without too much thought. It should be something that we can do. SOHCAHTOA. You shouldn't have to be drawing little triangles and looking things up. At the start of your A-level, that's okay, but by the end of the A-level, it should just be second nature. So there we've got our components bx and by. And I could draw my completed diagram. So here I've got A, and then I've got B's x component, which we've just calculated as 18.8 meters, and B's y component here. We need to add A to B's x component to B's y component. We've got to add all those together, and that gives us this dotted angle here. Sorry, I have to go over the calculator a bit to make it fit. Well, the resultant, which here I'm just calling r for simplicity's sake, we're going to use Pythagoras. 10 plus 18.8 all squared plus 6.84 squared all under the square root gives you the magnitude of the resultant. No problem. You do the maths, you get 29.6 meters. The direction, I've chosen to use the Greek letter alpha for the direction of it. We're going to go arctan of the opposite over the adjacent. So I've kept it in this form so it's clear to see what's going on. Chuck that in your calculator, you get 13.4 degrees. And so you would express your answer as 29.6 at a direction of 13.4 degrees to the horizontal. And that's all there is to say about adding vectors. Now you can go and practice some yourself. This QR code, hopefully the link is still live. It goes to an Isaac Physics board full of vectors questions. If it's no longer live, then you can look for those questions yourself. Moving on to algebra. Algebra in GCSE level is quite straightforward. Most of the equations that you manipulate have just 3 terms. But there are some that you manipulate at GCSE level with more terms. Even things like half mv squared is a little bit more complicated. Or v squared equals u squared plus 2as. It's a little bit more complicated. So at A level, it's assumed that you are fluent in algebra. A lot of this you're going to know, of course, but I do see students every year who try to use these formula triangles, these dastardly formula triangles, to solve their algebraic issues. It wasn't good enough for GCSE level. It's definitely not good enough for A level. So we do need to forget about crutches like that and learn to use algebra properly. Now, it's not too tricky. Just remember what the equal sign means. Of course, the equal sign means the same. But it's not just the magnitude that's the same on both sides of the equal sign. It's also the direction, the dimensionality. Importantly, the equal sign doesn't just mean, and here is the answer. That's what primary school children often think. They write an algebraic problem, maybe they write 6 times 4, and then they'll put an equal sign, and in their head the equal sign indicates the answer is. That's not what equals means. It does mean it's the same on both sides. So you can do maths on both sides simultaneously. And whatever you do to one side, you must also do to the other side. But you need to know the order that operations are performed in order to get it right. So there's a few different mnemonics to help people remember this. I'm not a fan of mnemonics. I think that they are all crutches, and some of them are helpful maybe in the early days, but you need to really internalize some of this stuff. So the first priority is always what's inside parentheses or brackets. My problem with this is that when people learn a mnemonic, they think anything to do with brackets comes first. It's only what's inside brackets that comes first. You're multiplying something by a bracket, what's inside the bracket has to be handled first. The second priority is any powers, and there's so many words that mean the same thing. Powers, orders, logarithms, exponents, indices. The singular of indices, the singular is index, not indice, which I've heard before. Third priority, multiplications and divisions. I mean, division is just multiplication with a negative exponent. So they're the same priority. Neither has more priority than the other. The fourth priority is additions and subtractions. Remember, subtraction is just adding a negative number, so they're equal priority there. And you might have heard of PIMDAS or POMDAS or PODMAS or PEMDAS, or my personal favourite, which is PPPPPP. PPPPPP is parentheses, powers, products, portions, pluses and purges. That's my favourite one. And it just shows how pointless these mnemonics are, because PPPPPP doesn't really tell you very much. So let's have a look at this problem. You can't do algebra if you don't understand order of operators. Here I've got 9 plus 2 times 4. Now, some people will be shouting at the screen saying, "Sir, it is 40." Others will be saying, "No, sir, it is 17." Some people will even be reaching for their calculator as though their calculator knows better. Calculators do make mistakes, and calculators do often disagree with each other. I am quite a fan of calculators. I have my own collection of them. They do behave differently depending on the calculator you pick up. So, what is the convention? Well, the convention is that we do our products first. So our product, 2 times 4, is 8. We can rewrite 9 plus 2 times 4 as 9 plus 8, which is 17. So there is only one correct answer to that, 17. That's if we're following the accepted standards for mathematics, which why wouldn't we? So here's another one, 10 times 2 divided by 4. Some people will be shouting at their screen, saying it's 5. Some people will be shouting at their screen, saying it's 20. I will take a moment to decide for yourself. Is it 5 or 20? Again, there is a correct answer. But in this situation, because multiplication and division have the same priority, it's not a case of multiplication comes first or division. You know, if you do PEMDAS, the M comes before the D. But if you do PEDMAS, the D comes before the M. So you're going to get people saying, well, you should do division first or you should do multiplication first. No, they're the same priority. So where you have two operators of equal precedence, you work from left to right. So first of all, we're going to do 10 times 2, which is 20. Then we're going to divide it by 4 to get 5. Now, what's nice is that some calculators are going to do this. You type something in and it will shove some brackets in for you or something to try to help you. And the classic example, as you can see here, is when you use implicit multiplication. That is to say, I've put two quantities next to each other with no operator between them, and multiplication is implied. We do have to be careful of doing this because sometimes brackets aren't used in this way. If you're working with functions, for example, f open bracket and then a bunch of letters, then close bracket, what's in the brackets there are the variables of that function. They're not multiplied by that function. So the notation of brackets we have to be careful with. This one did the rounds on the internet a few years ago because different models of the same brand of calculator, different models of Casio calculators gave two different answers. If you typed in exactly as it said, they would appear exactly the same on the screen. 9 divided by 3, open bracket, 2 plus, or 1 plus 2, close bracket, equals, and one calculator would give you a 9 and another calculator would give you a 1. Well, there is actually a correct answer. The correct answer for this one is 9, because you're working from left to right. And so 9 divided by 3, that's 3. Then that is multiplied by, okay, that's the implicit multiplication, that's multiplied by this thing. Remember, you do what's inside the bracket. Just having a bracket doesn't mean you do it first. You do what's inside the bracket first, which is 1 plus 2. So this bracket is 3, so you've got 9 divided by 3 times 3. Well, if I take 9, I divide it by 3, then I times it by 3, I've got 9 again. It's the same thing. If you wanted it to be 1, if you wanted this implicit multiplication here, to be done before that division, you'd have to chuck some extra brackets, and it's that some modern calculators will do for you. If you enter something with ambiguous notation, it will change what you've entered. You do have to check back and see whether the calculator has interpreted your input as you intended it. Don't assume that the calculator can read your mind. They're very clever things, but they cannot do that. So that's in terms of using calculators and order of operations. Actually, using the calculator causes students to lose a lot of marks. It's one of the biggest causes of lost marks I'm an examiner, as I often say. It's one of the biggest causes of lost marks is students not really understanding how their calculator performs operations, what order it does it, and how it's going to calculate something. Well, if your calculator's doing things differently, how do you know what you're going to get out? How do you know that the calculator is working for you? That's terrifying. The idea of having a calculator where you type in an expression and you don't know if what it's told you is the answer to what you wanted it to tell you, or if it's interpreted your input incorrectly. So here's a solution, a nice easy solution. Break a big formula into steps and do those intermediate calculations. Always do a quick check to see what you expect the answer to be, and see whether the answer the calculator gives you is reasonable, even if it's just a quick order of magnitude check. Finally, in extreme case, if you're having problems because your calculator keeps on disagreeing with what you want it to do, well, get a different calculator. Now, I found this out very late in my physics career, that calculators kept giving me the wrong answer. My brain doesn't work like that. Actually, reverse Polish notation, RPN, worked for me. And I found a few students, not many actually, but a few students in my career who have picked up RPN and gone, actually, yes, this is better. This works for me. So don't be afraid to stand out and be different. You don't have to use the same calculator as everyone else. Caveat on that is when you get to university, you might have to, depending on the university. Some of them have strict rules about calculators that can and can't be used. If you're doing an apprenticeship, you're probably not going to use a calculator at all. You're going to use spreadsheets and Python or something like that. You're not going to use calculators. So, we want to make a variable a subject. What do? We perform the opposite operation on that whole equation to what's being done to that variable. If there's more than one operation that's being done, we need to unravel them. We need to do them in reverse order, which is why it's important to know the orders inside and out. So here's an example for example. That's good. We want to make x the subject. We have this expression, 22 equals 4 times x plus 2. Well, in terms of operations, in order to get 22, we had to first multiply 4 by x, and then we had to add 2, because 2 comes, the addition of 2, comes later in the order of precedence than the multiplication between x and 4. You add 2 at the end. Not just because it's drawn to the right on this picture, but because pluses comes after products in the mnemonic. So what are we going to do? Well, first of all, we're going to do the opposite from the last thing that was done to our variable. Our variable was times by 4, and then it had 2 added to it. So we subtract 2 from both sides. 22 subtract 2 becomes 20, and all of this subtract 2 just becomes 4 times x. Now, what's the opposite of multiplying x by 4? Is dividing by 4. So we do that to both sides to get 5x. In the early days of doing algebra, you really do want to lay out all of those steps. It is important. Now, things to bear in mind with fractions. Okay, you don't want to embarrass yourself in front of your class by not realizing this, but I do see it all the time. 10 times 5 divided by 2 is the same as 10 divided by 2 times 5 is the same as 10 times 5 divided by 2. It has to be. Because what does divided by 2 mean? It means that division symbol, and then the 2, and you could put that anywhere. It doesn't matter, because multiplication and division have equal precedence. So it doesn't matter where you put it. So all of these three are actually the same. You don't have to believe me, you can check it for yourself. They're all equal to 25. 10 times 5 is 50, divided by 2, 25. 10 divided by 2 is 5 times 5, 25. 10 times 2 divided by 5, 5 divided by 2, sorry. 5 divided by 2 is 2.5, times by 10, that's 25 again. They're all 25. So, one way of dealing with this is to use negative powers and multiplications, and you can see it doesn't matter which order you put this in. That's one way around it. Another way around it is to get busy with the brackets. Use a lot of brackets. Don't do fractions of fractions if you can help it. So here you can see 200 divided by 20 divided by 2, or alternative, 200 divided by 20 divided by 2. Well, they sound almost the same. Indeed, they look almost the same. If you've got a very keen eye, you'll spot that this 200 divided by 20, the division is slightly shorter than the one beneath it. Whereas this, the division here is slightly longer than the one beneath it. But in handwriting, that can be very difficult to spot, especially in the heat of an exam. So let's get out the habit of doing that. If you chuck some brackets on this, to see how it should be interpreted, you'll see you get two very different numbers. You've got to be careful. Another alternative way of dealing with that is to use your negative powers. If you intended 200 divided by 20 first, and then divided by 2, that's this. 200 divided by 20 divided by 2. In fact, you can do that in any order, and that would give you 5. But if you intended 200 divided by half of 20, 20 divided by 2, then you could do this. There's a bit of a mess, of course, but you could do this. You've got your 20 here on the bottom, and then you've got this 2, which is a denominator, but it's a denominator of a denominator, so there's still a negative 1 power there. And that gives you 20. Or alternatively, you could have put the 20 divided by 2 all within a bracket. And so this is 20 times the reciprocal of 2, that's 20 divided by 2, and all of that is on a denominator, so to the power of negative 1. And all of these expressions mean the same thing, they mean 20. So a bit of a summary of inverse functions, here they are. Opposite of multiplication is division, opposite of addition is subtraction. We've got here powers. The inverse of a power a power is a root, so the second power, or squaring something, the inverse is a second root, or a square root. And there's another way of writing that, which is a fractional power. A square root is a power of a half. A cube root is a power of a third. That's another way of writing them. We also have your trig functions and their inverses. Sine, cosine, tangent, arcsine, arccosine, arctangent. And your calculators may say sine to the minus 1, but that's an ambiguous notation, so I avoid it. So the power of minus 1 means the reciprocal. It can mean the inverse as well, but it's because of that ambiguity that if I can avoid ambiguity, I will. And that's a good habit to get into. So I always write arcsine, arccosine, arctan instead of using the negative 1 notation. My favourite calculators just say ASN for arcsine, ACS for arccosine, and ATN for arctan. They don't use the minus 1 notation. And finally, one at the bottom here, which we'll have to go into in a little bit, is logarithms. N to the power of A equals B is actually the inverse of log to the base, bad wording, log with a base n of B is equal to A. Those two actually mean the same thing, but we'll need to handle logarithms separately. So in the meantime, you can practice your algebra. Hopefully this link is still live. Hopefully this page of Isaac Physics questions still exists. If it doesn't, you can find those Isaac Physics questions or other questions that you can use to practice algebra. Wolfram Alpha, for example, has a wonderful worksheet creator that you can use to just practice algebraic manipulation. Logarithms. Another very tricky skill that was suddenly going to hit you in A-level, and some students will have studied it at GCSE, some might not have done. I think everyone should have done, but I'm always surprised by how few people have studied or understand what logarithms are. So let's start by doing some examples. And I'm hoping these are all quite easy to follow. 10 to the power of 3, otherwise known as 1,000, and 10 to the power of 2 is otherwise known as 100. Okay, 10 to the power of 2 is 10 times 10, it's 100. 10 to the power of 3 is 10 times 10 times 10, so that's 1,000. And if I times those two together, I get 100,000, which is 10 to the power of 5. I could pick a different example. Here's a different example. 10 to the power of 4 times 10 to the power of 3. 10 to the power of 4 is 10,000. 10 times 10 times 10 times 10. 10 to the power of 3 is 1,000. 10 times 10 times 10. And so if I times 10,000 by 1,000, I get 10 million, which is 10 to the power of 7. Now what you'll notice is that, taking the first example, 3 plus 2 is 5. Taking the second example, 4 plus 3 is 7. So a general rule we could say is that 10 to the power of a times 10 to the power of b is going to be 10 to the power of a plus b. Or, more generally, n to the power of a times n to the power of b is equal to n to the power of a plus b. Now in that last example, n is called the base, and a and b are called the logarithms, or the exponents, or the powers, or the indices, or the orders. But n is called the base. So what about dividing your numbers, your powers? So we've got 10 to the power of 5, which is 10 times 10 times 10 times 10 times 10, so that's 100,000. Divide it by 10 squared, which is 10 times 10, which is 100. So 10,000 divided by 100, try again, 100,000 divided by 100 is 1,000. That's 10 to the power of 3. Do the same thing with the next line. 10 to the power of 4 divided by 10 to the power of 2. That's 10,000 divided by 100. That's 100. That's 10 to the power of 2. And you can see here the general rule. 5 subtract 2 is 3. 4 subtract 2 is 2. And you could do this with any numbers, just test it for yourself. 10 to the power of a divided by 10 to the power of b is 10 to the power of a subtract b. Or more generally, doesn't have to have a base 10, it could be any base. N to the power of a divided by n to the power of b is equal to n to the power of a minus b. Now some people will be saying, no, these aren't logarithms, these are the laws of indices. But it's the same thing. Logarithms are just another way of writing the same thing, writing numbers in a different way. So we could write the same number here, 10 to the power of 2, as 100. What this notation says is that the logarithm, when you've got a base of 10 that is equal to 100, is a logarithm 2. Okay, remember that logarithm is just another name for power. So this function, log, returns the power on that base that is equal to this value. Base 10, the power of 2 is equal to 100. So the logarithm on the base 10 that is equal to 100 is 2. That is the power. And you can see the same thing here. 10 to the power of 3 is 1,000. So the logarithm with the base 10 that is equal to 1,000 is 3. And 5 squared, 25, no problem. So the logarithm on the base 5, that is 25, is equal to 2. And you can see, you know your 5 times table. 5 25s are 125, and so this works as well. So in a general rule, if n is the base, n to the power of x equals y, then log base n of y equals x. Now that is true for any base, but if we use base e is just a number, e is a very, very special number, but it is just a number. E, Euler's number, to the power of x equals y, that's what we call the natural logarithm. The natural logarithm. And so we can use ln, lowercase l, lowercase n, for the natural logarithm. E, by the way, I've just looked it up just because I can never remember it, 2.71828182884 blah 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 46 something something something, doesn't matter. It's one of those transcendental numbers, but it rounds to three significant figures to 2.72. Bit of a weird number, but it appears a lot in mathematics and statistics and physics, so we might as well get used to it. So we can use ln, which is the same thing as log with the base e. Now, inverse functions of logarithms. We briefly looked at this when we did algebra, because we had to know inverse functions. It's how to get from one to the other. Okay, so I've just reminded you of this notation we've just looked at here. So if we want to get x out of the n to the power of x, we do the log base n of n to the power of x, because that will return x as a value. Now you can see that here. 10 to the power of 3, if I want to calculate what the 3 is, I do log base 10 of 10 to the 3, because that will be equal to 3, because 10 to the power of 3 is 1,000. So if we want to get n to the x from a logarithm, this is where it gets weird, we do n to the power of that logarithm, all of that. So raising something to a power is an inverse function to the logarithm of the same base. Bit of a mouthful, bit complicated. Let's have a look at a few sort of examples here. Don't know if this helps you at all. Maybe it does, maybe it doesn't. Log to the base 6n to the log with a base 10 of 10 to the power of 1. That's just log with a base 10 of 10, which is 1. Log with a base 10 of 10 to the 2 is going to be log of a base 10 of 100, which is 2, which is actually also 2 times log of the base 10 of 10. You can see that from the first line. That's interesting. Hang on a minute, that's interesting. Log with a base 10 of 10 to the power of 2 is the same as 2 times log with the base 10 of 10. Does it work for anything else? Well, let's try it with 100. Log with the base 10 of 100 to the power of 2, that's that number there, which is 4, which is just 2 times 2, which is 2 times, well, the log with the base 10 of 2 was this. So that's interesting. It's almost like we've taken that number 2 and moved it down to the start. Let's do one with a different logarithm. Let's do one with a logarithm 3. Log base 10 of 100 to the power of 3. 100 to the power of 3 is a million. So that's 6. Well, what is 6? Well, 6 is just 3 times 2. And what's 2? 2 is log with a base 10 of 100. So it's like we've taken that 3 and moved it down here. So a general rule here at the bottom, we could say, if we want to figure out what y is, and we've got log with the base n of x to the y, that's the same thing. It's equivalent to y times log with the base n of x. Does it work with anything else? Well, yes. Do you remember our laws of indices where we were adding logarithms? It works here as well. Okay, so log with a base 10 of 10, that's just 1. Log of a base 10 of 100, that's just 2. And what's 1 plus 2? That's 3. That's log with a base 10 of 1,000. Well, 1,000 is 10 times 100. So log with a base n of a plus log with a base n of b is equal to log with a base n of the product a and b. It has to be. Actually, what we're doing here is just using our laws of indices and writing it in this logarithmic form instead. This is really useful for splitting things up. And here we've got log with the base n of a minus log with the base n of b. And you can convince yourself of this. If the addition is multiplication, then the subtraction is division. This is actually how old slide rules work. You're adding two lengths, but they have logarithmic scales on them. Maybe I'll do a video about slide rules. So here's a summary of everything we've looked at, how to get from x how to get x from n to the power of x, how to get n to the power of x from a log base n of n to the power of x, all the different rules that we've looked at, there it is on one page. So now it's time for you to practice it so you can become proficient. Here we are. Hopefully that QR code will work. Hopefully it will take you to the right page of Isaac Physics questions. If it doesn't, then there are other questions out there that you can find. An incredibly important topic for A-level physics is dimensional analysis. Now, this is actually part of the A-level physics specification, but for reasons I'm not sure of, it often gets overlooked, and yet it's such an important skill. And if it were up to me, this would be taught at GCSE level, because it really underpins what physics is all about. So it's so important to have a clear understanding of dimensional analysis. Let's have a look at dimensional analysis then. Any quantity that can be measured in nature, any quantity can be broken down into 7 base dimensions, and they're listed here: time, length, mass, electric current, temperature, amount of a substance, and luminous intensity. And the letters that are given for those dimensions, and they're all capital letters: T for time, L for length, M for mass, I, capital I for current. This is a capital theta for temperature. Can't use T because we've always used that for time. N for amount of substance, and J for luminous intensity. Now each of those dimensions has a base unit, what we call a System International, or SI unit. This is what the entire scientific community has agreed to use. So times will be measured in seconds, with the lowercase s as the symbol for that unit. Lengths in meters, masses in kilograms, currents in amperes or amps, temperatures in Kelvin. You can use degrees Celsius as well. Amount of substance in moles. And finally, luminous intensity in candela. But we're not going to be using luminous intensity really in A-level. I can't think of any time where I've seen it. I've seen all the others used, but not luminous intensity, so we'll tend to concern ourselves with the first 6 of these base dimensions. Now, some quantities are combinations of these. An area is 2 lengths times together, and so on. But you can't express any quantity that can be measured without it being some combination of these base dimensions. Now, from a physicist's perspective, some of these are a little bit bonkers. Temperature, for example, can be expressed in terms of the others. It depends on your interpretation of entropy. Same with the number of moles of a substance, the amount of substance. Does that need to be a dimension? It's just an amount of something, it's just a number. And luminous intensity is a similar situation. So some of them can be expressed in terms of the others, but it depends on fine differences between, let's say, chemistry and physics. So these are what the whole scientific community has agreed with, mainly to satisfy those damnable chemists. So here we go. Dimensional analysis. A few principles. The most important principle is that of dimensional homogeneity. Something is dimensionally homogeneous if the dimensions are the same on both sides of an equal sign. Now, there are times in physics where we're quite happy to break that, where we've got certain constants we set equal to 1 for convenience sake, but we will not be dealing with those until you're studying physics at university, so don't worry too much about that at the moment. You cannot add quantities that are not dimensionally homogeneous, and you cannot subtract quantities. That doesn't make sense. If I say to you 30 centimeters plus 5 seconds, I can't process that. That doesn't make any physical sense. You know, what's 7 kilograms plus a meter? It doesn't make any physical sense. But 2 kilograms plus 3 kilograms is 5 kilograms. That's fine. That makes a lot of sense. We can add masses to masses. We can't add masses to times or to lengths. It doesn't make any sense. So for clarity, when we use dimensions, or indeed when we use units, we can use square brackets just to make it clear that the letters we are writing are not equation symbols. That's important. M, for example, could be mass, but the unit with a lowercase m as its symbol, the meter, is a unit of length. And you can see here I've given a few other examples, displacement and the unit of time and period and the unit of temperature, or the dimension, should I say, of temperature, capital T. So we do need to be a bit careful. We tend to use capital letters for the dimensions, and units often have lowercase letters, but not always. Kelvin, for example, is a capital K, joule is a capital J, Newton is a capital N, Coulomb is a capital C. Now I come to think about it, we use a lot of capital letters for units, so maybe I shouldn't have said that complete nonsense. I'm not editing it out. Right, so what do we do when we analyse our dimensions? We would prefer not to use slashes if we can help it because of the ambiguity. We prefer negative powers. We can use the bullet operator, that's a dot halfway up, not a dot near the bottom of the line, that's a decimal place or a radix point with base 10. We'd prefer to use a dot part way up. That indicates a multiplication between scalars, or indeed a scalar product between vectors, but that doesn't matter. So meters per second is a unit. If I'm saying it's a unit, I could put square brackets around it for clarity, and it would prefer to be written like this. We can use a dot. Sometimes that can make it clearer. It's not really needed. The places where this becomes important is things like the unit for specific heat capacity, the joule per kilogram per Kelvin. You can write that like this, or you can write that like this, but you can't write that like this. It doesn't make any sense because, as we've already studied, the order of operator precedence, this would be joules multiplied by Kelvin and divided by kilograms, because multiplication and division, even if it's implicit multiplication, it doesn't matter. However, very often exam boards actually prefer this unit of specific heat capacity and dislike this unit of specific heat capacity, even though this one is correct and this one is incorrect. It's frustrating, but it's the way it is. So let's get rid of ambiguity and use negative powers. That everyone's happy with negative powers. Joules, kilograms to the -1, Kelvin to the -1. No one disagrees with that. We're happy with that. Although perhaps I'd put the kilograms in brackets and raise it to the -1, because you wouldn't want to think the kilo isn't raised to the -1. Don't worry about that. That's just me being super weird. So, dimensions of quantities. There's a displacement, there's a time. The dimension of a displacement is a length, and that can be expressed like this. That's the product of all 7 dimensions with powers. Now you'll notice that all except length, the power is 0. The power for length is 1. That gives you your L dimension. Fine, okay. We could do the same thing with time, which is dimension of t. All the other powers are 0. And a velocity, all the other powers are 0, except length, which is 1, and time, which is a power of -1, -1. Because velocities, speeds, are lengths divided by times. It could be quite useful to write this, but I wouldn't be writing things like luminous intensity, amount of substance, temperature, electric current. I wouldn't be writing them if there's no way that's ever going to be involved in the quantities that I'm investigating, because it's just a waste of time and it actually makes it even more confusing and untidy. So, I will go back one slide for a second. That last sentence, if you raise anything to the power of 0, it just gives you the number 1. But that number 1 doesn't have dimensions, so effectively we've got rid of the dimension. Right, so let's take some more exciting, or I've called here more exotic quantities, things like forces. Well, let's pick any old equation for force, F equals ma, and we can, instead of writing it as F equals ma, we can look at the dimensions. Well, the dimension of m is easy. It's a mass, so we can put that in square brackets. The dimension of a is a little bit trickier. Accelerations are lengths divided by the squares of times. If you get confused, remember the unit for acceleration, meter per square second. So there's our dimension, and we can put these together in the order TLM. I'm not going to bother writing all the other dimensions. That is the dimension of force. T to the minus 2, L to the 1, M to the 1. Nice and easy. Do the same thing for energy. Pick any equation for energy. Well, we could pick half mv squared. We could pick mgh. It doesn't matter. We could pick force multiplied by displacement, and we already know what the force is here. So if we're going to do force multiplied by displacement, we're just going to have another L, so this becomes T to the minus 2, L to the 2, M to the 1, which is exactly what we get. When I got there by using mgh, M is a mass, h is a length, and g is the acceleration due to gravity. And we already know what acceleration is because it's come from there. It gives you the same dimensions regardless of how you derive them, whether you use half mv squared, mgh, or work done equals force multiplied by displacement. It doesn't matter. It gives us the same dimensions, as well it should. So here I've got half mv squared analysed as well. Half doesn't have dimensions. It's just a number. There's no dimensions with it. So don't be confused when you get things like that coming up. Just leave it blank. Mass is mass, and this is the velocity squared. So the velocity was length time to the minus 1, but we've squared it. And now when we multiply this all out, we end up, well, look, it's all the same. That is the dimension of energy. Now let's get something much more exotic. So this is Coulomb's law. It tells you the force between two charged particles. Q1 and Q2 are the charges of them, and R is the distance between them. We've got this constant, 1 over 4 pi epsilon naught. Force just a number, pi is just a number. But what about epsilon naught? Perhaps we're interested in the dimension of epsilon naught so we can figure out what unit to give it, or understand the physical nature of epsilon naught. The first thing we're going to do, we could take our equation, and we're going to rearrange it so that epsilon naught is the subject. Now we can do that comfortably because we've been practicing our algebra. Then what I'm going to do is put our dimensions in. Q1 has dimensions current times time. Q2 has dimensions current times time. The number 4 has no dimensions. So that's no dimension raised to the power of -1, it's just nothing. We've then got pi, no dimensions. We've then got r squared, that's a length, but it's to the -2 because it's on the denominator. We've then got force, and we already know what force is, and that's to the -1 because it's on the denominator. Now we just combine them all. What have we got? 2 i's, that's I to the power of 2. How many t's have we got? We've got 1 t there, another t there. These t's are to the -2, but they're also to the power of -1. So that becomes t to the 4 in total. T to the 2, t, and t is t to the 4. And L to the 1, that's actually to the -1, so that becomes L to the -1 and L to the -2, altogether L to the -3. So we now know the dimensions of epsilon naught. Now, why would we ever want to do that? Well, one way is to check equations are right. And that's an important thing to be able to do, especially if you're coming up with equations yourself or you're half remembering things. Why else would you want to do it? Well, you might want to do it to convert units. That's such an important skill. Or maybe even to derive equations for yourself. Brand new equations that have never been given before. So we're going to go through, we've looked at checking equations. Let's have a look at a few others. Let's have a look at converting units. How do we use dimensional analysis to convert units? Well, let's convert a length into inches. It's an older unit, but it still does the rounds. 1 inch is 2.54 centimetres by our modern definitions. So if we wanted to convert a length of 5.5 centimetres into inches, then I need to do something to that length, without changing what it is. Now, you can multiply any quantity by the number 1 and it doesn't change the quantity. As long as the number 1 has no dimensions, no direction, none of that, as long as it's just the number 1, it doesn't change anything. So the thing represented by 5.5 centimeters, that's a physical length. If I multiply that by 1, I have not changed that physical length at all. Well, we have said that 1 inch is equal to 2.54 centimeters. That is equal to. Which means that 1 inch divided by 2.54 centimeters is equal to 1. Great, let's times by 1 inch divided by 2.54 centimeters. Now the centimeters cancels on both sides of the equation, and I am left with 2.17 inches. There's a little note here about rounding. In our calculation, we used 5.5 centimeters. That's 2 significant figures. So we should have rounded our answer in the end to 2 significant figures. But we might keep 2.17 inches rather than just saying 2.2 inches written down, so that if we have to use that in any subsequent calculations, we'll use the unrounded number, or at least the less rounded number, because that's going to reduce the risk of accumulating rounding errors. We don't want rounding errors if we can help it. Here's a unit conversion that is first met usually at the very beginning of year 12. We know that joules is a unit of energy, but there's another unit of energy called the electron volt, and you become convinced that 1 electron volt is equivalent to 1.60 times 10 to the negative 19 joules. 13.6 electron volts, which is the ionization energy of hydrogen, that's in the ground state. How do we ionize, or how many joules do we need to ionize that hydrogen? So we need to multiply 13.6 electron volts by the number 1. What is that number 1? Well, it's going to be this way around, so that we're cancelling out the EV and leaving just the unit of joules. So that's a fun little way of converting. It's important to lay it out clearly so you don't get confused. It says here, you're multiplying a length by, you're dividing a length by a length. So the quotient, that's what you call it when you have one number divided by another, of two lengths, is going to be dimensionless. It's also going to be equal 1 if the two lengths are equivalent to each other. The quotient of 2 times is also dimensionless, and so on. So that's just saying what we've already said. So here is a really fun conversion. This is Pascal as a unit of force to pounds per square inch, PSI. And that's pounds force per square inch, not pound mass per square inch. Imperial units were very funny things. Well, what's a Pascal? It's a Newton per square metre. Fine. So we need to get rid of some of this, don't we? Let's first of all get rid of the newtons. We know that 1 pound force, we're given the conversion. We want to cancel the newtons, so we multiply our number by 1 pound force divided by 4.45 newtons. That's just the number 1. The newtons cancels. In terms of lengths, we want to get rid of the meters squared. Well, I've got a conversion into inches, but that's for centimeters. Well, 1 metre is 100 centimetres. That allows me to cancel one of the metres, but if I square all of that, I'm able to cancel both of the metres. And then I do the same thing to cancel the centimetres and give me inches. And if you express all that using numbers, you end up with 14.7 psi. You'll find at petrol stations and things, the unit psi is still used for pressure in tyres. So it's not a dead unit, it's just an old unit. Right, so here's a fun use of dimensional analysis. Deriving equations. So if we want to derive the drag, the fluid drag, on a sphere moving through a fluid. So it's like air resistance, but it might not be air resistance. It might be water resistance or oil resistance, or it could be air resistance. We have to first of all think, what does it depend on? Well, it depends on probably the size of the sphere. Maybe we can say area, maybe we can say diameter, it doesn't really matter. Probably depend on how fast the sphere is moving relative to the fluid, and the density of the fluid might have some effect? We think that's what it depends on. Well, the dimensions of all those quantities are there. Density is a mass divided by a volume, so that's expressed here. I've kept the t's here because I think, and the m's where there's zeros, because I think that'll make it clearer. And we think the equation, it's not going to quite be an equation because we don't know what the constant of proportionality might be, but we think that force is going to be proportional to something to do with diameter, something to do with velocity, something to do with density. And I've used A, B, C as those powers. Let's calculate what A, B, and C are. So we can first of all write out our dimensions. There we go. Exactly what we had. So instead of writing the equation, we put that the dimension of F is that, and that has to be equal to. If these are proportional, then it has to be equal to. This is the dimension of the diameter of the sphere, which is just L, to the power of A, because diameter to the power of A. And this is the velocity, L divided by T, to the power of B, and so on. So now what we're going to do is try to find out what A, B, and C are. It's a puzzle to solve. It's not a difficult puzzle to solve, really. We could look at mass, first of all, and say that must be homogeneous. And this term has mass in it, and this term has mass in it. And so, because this term is mass to the 1, then C must be equal to 1. And then we could look at another quantity. Let's just pick one. Let's pick temperature. This is 0, this is -1, that's 0, that's -2. So B is going to have to be 2 to get time to the -2 on the right and time to the -2 on the left. And then finally, we can look at length. And we go, well, there's -3 and 1 and 1. So at the moment we're on the right-hand side. Well, what are we going to have to do? We're trying to change A, aren't we, here? So let's worry about A in a second. We've got 1 here, we've got 1 there, so that cancels. We've got -3 there, so I need to have more than that. I need to have another 2 of these in order to get to where I need it to be, so that means A is going to equal to 2. And you could double check this. 2 lengths, add another 2 lengths, that's 4 lengths. Subtract 3 lengths, so that's going to be 1 length, and that's 1 length. So you can double check. If you get lost, you can double check. Don't forget to raise L to the 1 to the power of 2, so that becomes L2. Okay, so that gives you your numbers, which you can then plug into your equation, or your proportionality anyway, and you get that. So it looks like drag is proportional to the square of the speed that a body moves through a liquid or a fluid. But what about viscosity? Well, we could do the same thing again, but this time let's consider viscosity instead of density of the fluid. The dimension of viscosity is given here. There's our equation. We can use it in the same way as we did before. A, B, and C, these are the dimensions for those quantities. And we can use that with some basic equations to figure out what A, B, and C are. First of all, let's look at mass, because mass only appears on the term with the power C on the right-hand side. And so C equals 1, and then just unravel all the rest of them. And the equation therefore looks like this. Ah, that's interesting. So now it looks like the drag force is proportional to the speed. But before, it looked like it was proportional to the speed squared. How interesting. So what if we do it for both viscosity and density? Well, that's where it gets a bit tricky. So we've now got an equation like this, which means there are 4 terms after the proportionality sign. We're using both viscosity here and density. Viscosity, remember, is basically it's an indication of how difficult it is for the fluid to get out the way as something moves through it. So that feels like it should be relevant to this. So there's our expression. Now the problem with this is, if we try and write down some simultaneous equations for time, length, and mass, which we've just done there, we've got a problem. There are 3 equations because there are 3 dimensions that are relevant, but there are 4 unknowns. That means there's more than one solution. Infinite number of solutions. So A, B, C, D, what I've done here is I've just said that there are -2 times on the left equals A no, there's no time there. So negative 1 lot of B, negative 1 lot of C, and there's no times there. So that's how I've got that equation, and I've done it with the other two as well. Now this is a problem. 3 simultaneous equations, 4 unknowns. But we can find solutions, we just have to do a bit of guesswork. So we could, for example, just guess that because negative 2 equals negative B, or should I say minus B minus C, that maybe B and C add together to make minus 2, so maybe that's going to be minus 3 halves minus a half, which is what we have there. Or we might start from the third equation there, 1 equals C plus D. Well, maybe C and D are just a half each. That would work. Why not? So we can try some things. So we can get a solution by doing that, which you can see we've got there. I think it's the same slide as last time. Yes, I should have deleted that slide. We have the same thing. We get a new equation like that. We can plug those powers in, and we get something that looks a bit like this. You can actually get to that equation just by multiplying together the previous two equations, actually. And that's how things should work. The drag force for density and the drag force for viscosity. You just times it together, you can get this equation. We still don't know what the constant is. So this works dimensionally. It might not be right, of course, but dimensionally it works. So that's fine. All 3 of those are dimensionally equivalent. They are homogeneous. Which one we use becomes a matter of physics, or maybe even engineering. It's something we have to think quite carefully about. Very often we're actually going to use this equation. Not always, but very often we're going to use that equation where we say that the air resistance is proportional to the square of the speed that something moves through the air. But not always, and in fact the first equation appears in the turning points option of the AQA physics A-level. It's Stokes' law for viscous drag, but we're not going to talk about that during this session. We're just looking at dimensional analysis. I've included this problem now, the Galileo study of whether giant animals are possible, because this often gets described as a use of dimensional analysis, but we don't really need to see it that way. You know, we could just have a look at some basic ideas. You don't need dimensional analysis for this, really. Yes, we can have giant animals, but it doesn't just look like a giant ant from the old sci-fi thriller film Them, which is where this slide comes from. I'm hoping I've got fair use rights to use this slide, or this screenshot of a giant ant in Greyditch in Fallout 3. Again, I think this is fair use. So let's just consider animals with bones. Let's just consider animals with a femur. And it's fair to say that the size of the animal is probably going to be related to the length of the femur. And I'm going to use the lowercase l. Curly L is how we write that, so we don't get it confused with the number 1 or the capital I. So that's a curly L for the length of the femur. The diameter of the femur has probably got something to do with how strong the femur is, and that's probably going to be important. So let's have D as the diameter of the femur. So we reckon that the strength of the bone is going to be related to the area of the bone, the cross-sectional area. We also think that if the bone is more massive, it's probably going to be stronger as well. The height of the animal is going to be related to the length of the femur. The mass of the animal is going to be related to the mass of the femur. That kind of makes sense. Mass of the animal proportional to the volume of the animal, and therefore the volume of the femur. It all kind of makes sense. And so the volume of the animal is proportional to the volume of the femur. So we're kind of just having some guesses at things to do with these giant animals. And then we can have a look at the relationships. So we want the bone to be strong enough to support these animals. Some set constant amount of strength of bone that is sufficient. So let's just call that S and say S is proportional to D squared. That's what we had before on that list. The mass of the animal is going to be related to the volume of the animal. Of course, it's going to be the density multiplied by the volume of the animal. But that's going to be related to the volume of the bone. So that's L squared. It's related to L squared. It's not exactly going to be L squared. Probably going to be more like sort of LD squared. But it doesn't matter. We're just taking this as a rough idea to get the dimensions. And then we can say that the strength of the bone is related to the mass of the bone. And if we chuck these ideas together, which we can do, you can see there, we've got an M here and an M here, we've got a D here, we've got an S here and an S here. We can put these equations together. The constants, I don't know what they are. It doesn't really matter. They're just turning things from proportionalities into equations. So we can combine the equations, then we can combine the constant, and you end up with something that looks like this. L cubed equals CD squared. Now this isn't just animals, we do this with buildings. If you increase the height of a building, you have to increase the area at the base of the building to keep it strong. And we use this law we're now currently deriving all the time in engineering. And so you can see L is proportional to D to the power of 2/3, or D is proportional to L to the power of 3/2. It's just working with these powers, and the constant is changing accordingly as well. And we can do some comparisons. You know, we could say we've got two animals with the same basic shape and the same strengths of their bones, and the same basic shape means that C is the same. Then we've got animal 1 here and animal 2 here. And if we divide one equation into the other, you get this. And the constants cancel out. That's convenient. And that's dimensionally consistent because either side of the equal sign has no dimensions. And you can take the powers outside. And you can do things like this. So we can now see the relationship between the ratio of heights of animals and the ratio of widths of their legs. And it's not a proportional relation. Well, it's not a linear relationship. You know, we could make the diameter of the femur, so the diameter of the leg, the subject, and see how that's related to the height of the animal, or the length of the femur. This is called the square cube law, and as I say, it works for animals, but it also works for other things as well. It means the taller it gets, the leg diameter has to get larger, but not in a linear relationship. So let's look at an example. If I want an animal that's twice as tall, the leg ratio is going to have to be 2.8 times, almost 3 times the diameter of leg for the animal to be twice as tall, but still have the same strength of bones in the leg. If the length of the leg is 3 times as tall, so 3 times as high the animal, now it's going to have 5.2 times the diameter. So how do we address this? Well, we don't have the same basic shape of animal. We don't. That's why elephants look very different from ants. But with buildings, this tells you why you have to have a much wider base if you're taller, or do some very clever engineering tricks. And that's everything I wanted to talk about with dimensional analysis. This QR code takes you to some Isaac Physics questions, if the link is still working. If Isaac Physics has moved some things around, it won't work, but you can find those questions yourself. So have a crack at those, and then we can move on to the next topic. Let's have a look at graphing skills. GCSE level, I see all sorts of terrible graphs, and we're just going to assume that you can graph things properly, but there's more than that. Graphs serve a purpose. We draw them for a reason, and that reason is to extract data. Now, in physics, we like straight line graphs. Everything we do in physics, in practicals, is going to be trying to get straight line graphs. And if a relationship isn't a linear relationship, we're going to modify things to make it so it is. Now, straight line equation, depending on where you live in the world, it will be one of these three, probably. Y equals mx plus c is what I'm going to use throughout this video. But if you live in a part of the world where they use a as the gradient and b as the intercept, or b as the intercept, b as the gradient and a as the intercept, then just adjust what we're doing accordingly. This is what we use in the UK, so that's what I'm sticking with. So we're going to try and get our equations into the form y equals mx plus c. Now there are some very few equations where we are quite happy with curves and things. Maybe we're looking at sinusoidal relationships or something, but it's quite rare. Usually we're trying to get straight lines. But what I see when students plot graphs, even at the start of A-level, is things like this. You can zoom in if you like. For some reason, we're plotting distance versus time. Don't know why, doesn't matter. We're plotting distance versus time. And the students put a false origin, except they haven't. They've broken the axis. Never do this. Never do these zigzaggy lines. You don't need it. They haven't bothered with the units on the axes. I've had to label that. And they've done this dot to dot with dots instead of X's and connecting lines. And it's just rubbish, because the data doesn't take up enough space at all on the paper. Now, what we want is we want it to space out the data. So we have to use false origins where we can, and we want to ideally have more than half the paper filled with data points vertically and horizontally. We can use gradients. We can measure gradients when we've got false origins, but we can't measure y-intercepts. So we have to then calculate the y-intercept by using y equals mx plus c. And as I've said there, never break the axes. So this is a better graph of the same thing, the same data. And you can see we've now got our false origin. This is good, little tick. There's no breaking the origin, no zigzaggy line. Data just about occupies the vertical space. The scale could have been extended out, I suspect. It just about occupies it. Maybe. Units are there. Units are after the slash, by the way, because we want our quantities to be dimensionless on the axes, because we are representing those quantities as lengths. We are representing this time spatially as a length. So to make sense of that, what we're going to do is we're going to divide by the unit of time so that what we're plotting is just a number. And then we're going to represent that as a length. And this is already a length, but we do the same thing anyway. Line of best fit is a straight line. And when we calculate the gradient, notice that I've drawn little circles on the line, not near the x's. I've tried to avoid the x's. I've written the coordinates of those points. You can draw lines with the ruler back to the axes if you want to. I've done the gradient calculation, including the units. That's great. That's what we want to see. Okay. And when I do the intercept calculation, I use this point up here and the gradient I'd already calculated, because big values means less uncertainty, which we'll come to later. So when we do those gradient calculations, the triangle some people draw, but the points, the key thing is the points on your graph, as far away as they are, they need to be at least 8 centimeters away from each other vertically and horizontally. So that's important. Don't count the squares. Use the values from the x and y axes. Don't be counting squares. That's how you learn to do gradients in maths, but it's a terrible habit to get into. Don't count the squares. Not for gradients. We will for areas, but that comes later. And gradients have units. The unit of the y-axis divided by the unit of the x-axis. Gradients have units. So if we want to determine the y-intercept, as I've just said there, use large values of x and y and the value of m that you've just calculated. Don't use the data points, use the line. The data points have served their purpose once you've drawn that line. If you want areas, and there's some times where you're going to want areas, you've got a velocity time graph, for example, the area represents displacement. A second. If you want areas, you're going to have to count the squares. There are various other ways of calculating areas, but this is what we do in A-level. And then we multiply the value of a square by how many squares. And any part square counts as a half square. That's quite critical. Areas below the x-axis are negative. You can read that yourself. So here's a graph. This graph has distance on the y-axis, time on the x-axis, and for some unknown reason we're going to calculate the area of this. There's no physical significance of that. Don't know why we're going to do it, but let's do it anyway. Doesn't mean anything, but let's do it. So we're going to calculate the area. It's a curve. If it was a nice regular shape, we could use geometry to calculate an area, but because it's a curve, we're going to have to count the squares. So let's start with the big squares. We count the big squares there, and we know how many, there's 25 little squares in a big square, and so we've counted the big squares. Then what we can do is count the little squares that are whole squares, and I've written them on there so I don't lose track of them. And then finally I can try and count those little squares, those little squares that are all the way around the edge as half squares. And you can calculate the total number of squares, multiply it by the quantity represented by a single square, which in this case has no physical significance at all, units of meter seconds, whatever that is, and there we go. We've got our area. So that's how we do areas. Fine. So how do we get equations into the form y equals mx plus c? Well, remember that y equals mx plus c is a variable equals a constant times a variable plus a constant. You plot y on the y-axis, x on the x-axis, because they change. It'd be really boring if they didn't. And m must be a constant if it's a straight line. So that tells you what's going on here. Variable equals constant times variable plus constant. So let's take a nice easy example of something we want to get in that form. F equals ma. That's kind of already in that form. That's variable equals constant times variable plus 0. So we expect a y-intercept of 0, and the gradient would be the mass. That's nice and convenient. If we plotted it this way round, so if acceleration is constant, then we have to switch the a and the m around. Not a big deal, but we've now got m as the variable and f as the variable. But if f is the constant, oh dear, we have to do this. Now that's still f equals ma, just divided through by m and written it in the form variable equals constant times variable, and this is plus 0. So I would plot a on the y-axis and 1 over m on the x-axis. Or, if f is a constant, I could have plotted the axes the other way round, actually. M on the y-axis and 1 over a on the x-axis. And the gradient would still equal that constant force. Let's pick a different equation. Let's pick c equals f lambda. If f is the constant, we're already in the form y equals mx plus c. Nice and easy. We plot c versus lambda, then that constant f can be determined by measuring the gradient. But if the wavelength is constant, then we have to plot c versus f, and the wavelength will be the gradient. Nice and easy. But if c is constant, then we have to plot f versus 1 over lambda, or lambda versus 1 over f, and c will be the constant, c will be the gradient. Well, that's fine, but so far none of these have had a y-intercept, so let's look at one with a y-intercept. Let's look at v squared equals u squared plus 2as. Okay, well, if acceleration and initial velocity are constant, we're kind of already in this form. Although I appear to have messed up my colours a little bit. There we go. S should be green to indicate that it is a variable. So we plot v squared on the y-axis, s on the x-axis. The gradient is 2a. So if we want to know what a is, it's going to be half the gradient. We're just doing algebra. Algebra over here. You want to know what u is? Well, u squared is the intercept, so u is the square root of the intercept. And you can rearrange these equations however you like. You know, we could look at s equals half at squared. No problem. Well, the y-intercept is 0. That's boring. No problem. But what if we had a y-intercept? Well, this is a bit more complicated now, because look, we've got variable equals constant times variable plus constant times variable, if acceleration and initial velocity are constant. That's a problem. It's in the wrong form. So we're going to have to divide through by one of these variables to get rid of this constant times variable quantity. Well, given that this one the variable's t and this one the variable's t squared, t here, t squared here, it makes more sense just to divide through by t. If I divide through by t, I end up with variable equals constant times variable plus constant. So you can see I'll swap these terms around as well, just to get in the form y equals mx plus c. It's complicated. It is complicated, but it's a skill that you will need to acquire. It gets more complicated when we have logarithms. So a equals a naught e to the power of minus lambda t. What if a naught and lambda are constants? Well, the basic rule here is to get these in the form y equals mx plus c, you take the natural log of everything. And if you do that, and using your laws of logs from before, you get this, and that's in the form y equals mx plus c. Let's just write it the other way round, swap these two around. Plot this on the y-axis equals constant times, plot that on the x-axis, plus constant. Well, minus lambda is the gradient, so lambda is minus the gradient. And natural log of a0 is the intercept, so a0 is going to be e to the power of the intercept. Remember that the natural log and e to the power are inverse functions. Natural log and a power are inverse functions. So that's fine, but we've taken something that would have been an exponential decay and turned it into a linear graph. Really, really helpful. Or we've got this, a equals c times x to the power of b. And we're told that b and c are constants. Well, I've got no idea what b is. What am I supposed to do to find what b is? Well, if I use my laws of logs, I log everything. Log base 10 of a on the left, log base 10 of the right hand side, but because they're multiplied we can split it. Remember those laws of logs from before? And so I've also switched around the positions of these, so I've got plotting this on the y-axis, plotting this on the x-axis, and I end up with b being the gradient and log base 10 of c being the intercept, so c becomes 10 to the power of the intercept. We've got our equation. It's a power law, and we've made it a straight line, so we can determine what the power is. Really useful skill. Or something like this. A equals c b to the power of x. And we're told that b and c are constants. Wow, how are we going to find what they are? Same thing we did before. We just log everything, and then we arrange it so we've got a variable equals constant times variable plus constant. And you've split that log up using those laws of logs. So it's complicated. Yes, it is complicated, but it's well within your capability to do it. So, any linear relationship or any polynomial, you can just rearrange it, usually. If it's an exponential, you're going to have to do the natural log of one of the variables, or natural log of everything, actually, and then plot the natural log of one of the variables versus the other variable. And if it's a power law, you're going to plot the log of two variables. Trig functions, well, they're a little bit different. If you had a trig function like this, then you would have to plot y versus cosine of theta to get a straight line, where a would be the gradient. But you would still be able to do that. So it's a little bit different, but it's the same idea. You're just trying to get a straight line by doing algebraic manipulation into the form y equals mx plus c. And if you want to practice that, which you should, go and have a look at these Isaac physics questions, get cracking on some of them, see how you get on. And good luck to you. The last topic we're going to look at for GCSE to A-level physics transition is errors and uncertainties. Now, you already met some idea of errors in your GCSE. You met systematic and random errors, for example, and you would probably have had to estimate errors as well. So this is a bit of a reminder of that, because often those topics get skipped, but also it's going to help you with a little bit of a primer of how to handle errors. There's a lot here we can't go into, but it's going to be a good start for you by way of transition. So first of all, a little bit of terminology for you. Errors. It does not mean mistakes. There's no human error. There's no mistake here. The word error, it means that there is a difference between what's measured and what's the accepted value of some quantity, which some exam boards call the true value. For example, you measure the charge of the electron, and you measure it to be slightly different from what the rest of the scientific community says, then you have an error associated with your answer. And errors are inevitable. You're always going to get errors with measurements. You can quantify errors by giving uncertainties as a way of sort of quantifying your doubt in a particular value. So uncertainties have numbers with them. So I'll often use the term errors and uncertainties interchangeably. They are actually slightly different in meaning. It doesn't really matter. Uncertainty gives you a range. That's what the numbers are. It's a range of values where your value is within that range, and you kind of hope that the accepted value is also within that range. So it is tied quite closely to the idea of accuracy, how close your range of measured values are to the accepted value. It's not very accurate measurement if the accepted value lies outside your uncertainties. And precision. So precision's how close together your values are. Whether they're close to the accepted value or not is irrelevant. For precision, it's just how close together your values are. So accuracy, we have random errors, which cause a bit of spread. And you've also got systematic errors. We'll talk about what that means in a second. Precision is only to do with random errors, not systematic errors. So random errors, you're always going to get them with every measurement you take. Small variations in, let's say, for example, machine tolerances. You're building a particular, I don't know what it is, shelf, and you cut a piece of wood to a certain size, but there's always going to be small differences, and if you were to very carefully measure the length of your shelf in different places, it'll actually be slightly different lengths. Very, very tiny differences. Tolerance in your ability to cut things to the same length, and that's going to give you random errors when you come to measure that length later. So there's no direction to it. Measurements can be slightly higher, slightly lower than whatever an accepted value would be. Systematic errors have a direction to them, a statistical bias to them. So for example, if my balance that I'm measuring a mass on, it was broken somehow, perhaps it was calibrated incorrectly. So for every kilogram that I put on top of this balance, it tells me 1.5 kilograms. And if I put 2 kilograms on, it tells me 3 kilograms. Well, that's a certain amount. In this case, it's a certain proportion different from the accepted value of the mass that I'm measuring. And therefore, that is a systematic error. Or it could be that the scale's all shifted. So my balance, when there's nothing on it, say 0.5 kilograms, I place a kilogram on it, it says 1.5. I place 2 kilograms on it, it says 2.5. So the amount that it is wrong by is the same amount each time. So that would be a systematic error. Sorry, a systematic error. Random errors tend to be distributed like this. This is a normal distribution or a Gaussian distribution. If you haven't studied much statistics, the numbers on the x-axis aren't going to make tremendous amounts of sense to you. That's sigma there, which is one standard deviation. And so this is one standard deviation from the mean, this is 2 standard deviations from the mean, and so on. And on the y-axis is your probability of measuring that particular value. So the likelihood of measuring a value that's very close to the mean should be higher than the likelihood of measuring a value very far away from the mean. It should be. That's what we would expect a spread of measurements to be like. What is standard deviation? Well, you can think about it as the mean distance from the mean. It's a nice way of thinking about it, but we're not going to cover that in this video because we're only giving you an overview. So random errors do tend to be normally distributed, and you can simplify the calculation of them. Rather than expressing those random errors in terms of standard deviations, which you can do in statistics, and we do it in physics, in A-level physics, to keep it simpler, we use the same approximation as you used in your GCSE. So in your GCSE, you use this approximation. If you have a range of values, then you take your maximum value, the minimum value, calculate the difference between them, divide it by 2. Half the range would be your absolute uncertainty. Now, a little thing about that, these values have to be values of the same measurement or the same data point. You can't calculate uncertainties where there's a list. So, for example, if I am measuring different diameters of a wire, and it's the same wire, and I'm measuring different diameters at different points along the wire, and I expect it all to be the same, but I might get slightly different values. I can use this approach to measure the uncertainty in those values. On the other hand, if I'm doing an experiment where I'm dropping something, maybe I'm timing how long it takes to fall, and as it falls, I'm dropping it from different heights each time, so I expect it to take more time to fall each time. On my table of results, I'm going to have a whole bunch of different heights, starting from low heights, going up to higher heights. That I can't use this on that list to get an uncertainty in the height. That wouldn't make any sense, to get the maximum height I dropped it from and the minimum height I dropped it from. That's not what this is about. This is about uncertainties for a particular measurement that you will have repeated. Hopefully you'll have repeated it, but it's one particular quantity that we are measuring. So here is the example I gave of the diameter of a wire. You make multiple measurements in different orientations in different places, and you get perhaps 7 measurements, as you can see here. Well, the highest one was 1.03 millimeters, and the lowest one was 1.00 millimeters. So half of that range is 0.015 millimeters. That is your random error. That's your uncertainty presented as an absolute uncertainty in these values. You can't do it in this case. For example, if we're measuring the resistance of a wire as we change the wire's length, we can't just do 100 subtract 20 divided by 2 to get the uncertainty in the wire length. That doesn't work. That's not what we are doing here. So we do have to be a bit careful. Each of these rows is a data point. And if we had made multiple measurements of resistance for a particular wire length, then we could have an uncertainty for that particular resistance. But because we changed the wire length each time and only have one value of resistance for each, we can't really do very much with that. But we can estimate an uncertainty based on the instruments that we have used to measure. So, for example, if I used a ruler to measure the wire length, and in this ruler it could only measure to the nearest centimetre, and I used a resistance meter, an ohm meter, to measure the resistance, that could only measure to the nearest 0.01 ohms. And I've got these data here. Well, what I can do with this is I can estimate the uncertainty, and it's going to be based on the resolution of the instrument. Now, if I've got multiple measurements of the same data point, then I can do half the range. That's fine. But if I don't, and I still need to estimate the uncertainty, then I can do this. I know that this ruler could measure to the nearest centimetre. So that 100 centimetres data point here, that could be as low as 99.5 centimetres, or it could be as high as 100.5 centimetres. So that's a range from 0.5 centimetres below the 100 to 0.5 centimetres above the 100. But when I make a measurement, I'm also holding the ruler against two ends of that ruler, of that wire length, the ruler against both ends. So there's going to be about half a centimetre of uncertainty for each end, so that's combined to give me 1 centimetre of uncertainty. Now this is the case for all, I'm going to say all, possibly most, but certainly a lot of the analog instruments that we use to measure, is the uncertainty will be equal to the resolution of the instrument. Now with digital meters, digital instruments, it's possible to set the zero. You set that so there's no uncertainty on it. And so because you can set what zero is, then the uncertainty in that measurement is only going to be based on one reading, not the zero reading. And so, as you can see here, although the resolution of this resistance meter was 0.01, half of that resolution is what the uncertainty is in the resistance measurement, because in each of these resistance measurements, because I was using a digital meter. So if we're using an analog meter, then its uncertainty is equal to the resolution. If you're using a digital meter, then usually, because you can set the zero on it, it's going to be equal to half of the resolution. But you do have to use some intelligence when you're calculating these things. Okay, so that's just a summary of what I've just said there. You can read that yourself if you want to pause it and go ahead and read it. So I keep using the word absolute uncertainty. And what do I mean by that? Well, these are different ways of presenting uncertainties. We've got random error and we've got systematic error, but the uncertainty, remember how we're quantifying our doubt in a particular measurement, there's two ways of presenting that. We could present that as an absolute, which has units. So, for example, 10 centimeters plus or minus 1 centimeter, that is an absolute uncertainty. Or we could present them as relative or percentage uncertainties. And I use the same symbols for these. That is a Greek letter epsilon. So for absolute uncertainties, we use a delta. For relative uncertainties or percentage uncertainties, we use an epsilon. And the only difference is relative uncertainty is presented as a unitless decimal, and percentage uncertainties, they are presented as a percentage, remembering that the percentage sign just means divided by 100. So if you multiply a relative uncertainty by 100%, you're multiplying it by 1, but it means that we can express it as a percentage. So that's how we calculate them. And we can come to that in an example in just a little bit. But the point is, because relative uncertainties and percentage uncertainties don't have units, the percentage sign isn't a unit, we can deal with them in the same way. So they're pretty much interchangeable. If you want to calculate a percentage uncertainty, you just times your relative uncertainty by 100%. Then the percent sign hangs around and gives you your percentage. Now, this calculation, the absolute uncertainty we already know about. That's half the range. That's fine. This value in the triangular brackets is what we call the mean value. Now, if you only have one value, one measurement, and you've estimated an absolute uncertainty based on the resolution of the instrument, well, in that case, your mean value is just the value that you've measured. But if you have a range of values, like our diameter of the wire example before, then your mean value is going to be adding up all of those values and dividing by how many you've got, the usual way of calculating mean. So to calculate the relative uncertainty, we just do the absolute uncertainty and divide it by the mean. Percentage uncertainty, just as it says here. Now, this is the key idea, and you've really got to be clear about this. When you are combining uncertainties, whether we add the absolute uncertainties or whether we add the relative or percentage uncertainties, it depends on what we're doing with the quantities. If I'm adding two lengths together and I want to know what the uncertainty is in the combined length, well, because I'm adding the quantities, then I add the absolute uncertainties. Or if I'm subtracting one time away from another, because I'm subtracting two quantities with units, then the absolute uncertainties can be added together, not subtracted, added together. Whereas if I'm multiplying or dividing two quantities together, like f equals ma, I've got uncertainty in m and uncertainty in a, and I'm timesing them together, I can't add the absolute uncertainties together because that doesn't work. Because the absolute uncertainty in the mass will have units of kilograms, and the absolute uncertainty in acceleration will have units of meters per square second. And you can't add kilograms to meters per square second. We talked about that in the dimensional analysis section. So we have to add together the relative or percentage uncertainties because they are dimensionless and they have no units. So let's look at an example. Here's two lengths, two wooden beams, and we want to add the lengths together for whatever reason. Well, we're going to measure the lengths of the beams, and that's easy enough. You just put them against some rulers and you measure them. And the top one looks like it's about 7.5 centimeters, and the one beneath that about 13 centimeters. And you add them together and you get 20.5 centimeters, and everyone's happy. However, that was okay at GCSE level. Let's look a bit closer. And for each measurement, for both of those lengths, there was 0.5 millimeter of uncertainty about this position. As long as the edge of this wooden beam was closer to 0 than it was a millimeter before or a millimeter after, then we call that 0. And we can't assume it's dead on 0. We just can't do that. So that is a reading of 0 plus or minus 0.5 millimeter. That's what that is. You can't say anything other than that. On the other side, let's just take the beam that was about 7.5 centimetres long. That was 7.5 centimetres, give or take half a millimetre. That's what it's got to be. So if I had the longer one, that would be 13 centimetres, but give or take half a millimetre. And I'm being consistent with my units here by giving centimetres as the unit for the uncertainty, but converting centimetres and millimetres is not too tricky. So because we've got two readings for each length measurement, the zero reading and the reading at the other end of the beam, then we have to add together the uncertainties in those two readings, the absolute uncertainties in those two readings, because they're both lengths, and we get 1 millimetre of uncertainty. But that's 1 millimetre for each beam. So because we're adding together the lengths of the two beams, we also have to add the uncertainties together. The shorter beam was presented like this, the longer beam presented like this, and this symbol here is the plus or minus symbol. You might be familiar with that from square roots. Square roots have two possible values. It could be positive or negative a square root. But there we go. So, because if you square a number that's negative, you'll get the same thing as if you square the same magnitude number that's positive. So plus or minuses you'll be familiar with. The combined length is easy. We just add the means together, 7.5 plus 13.0. But the combined uncertainty, we add these two absolute uncertainties together, so our final length measurement we would express as 20.5 plus or minus 0.2. Actually, we wouldn't. We'd give our uncertainty to two significant figures, and that's not normal. That's not something that happens in the real world of physics. That's what happens in the little walled garden of A-level physics. In the real world of physics, one significant figure uncertainties are perfectly fine, but let's go with two significant figure uncertainties. But we'll talk about that a little bit later. This is an example of wave speed calculation. So in wave speed, we're multiplying together frequency and wavelength. And let us suppose that I've got the wavelength and the frequency expressed like this with absolute uncertainties. And we're asked, what does the wave speed equal? Well, I can easily calculate the wave speed mean just by taking the mean wavelength, that's 0.770 meters, and multiplying it by the wave frequency, that's 440 hertz. When I do that, I get 338.8 meters per second. Okay, fine. But now I've got to combine the uncertainties. And the problem here is that the uncertainties are absolute uncertainties, which means I've got to convert them first into relative or percentage uncertainties. The quantities are multiplied or divided. That's the first step. That's what we have to do. So to calculate the percentage or relative uncertainty, we do the absolute uncertainty divided by the mean for each of these quantities. Epsilon lambda means the relative uncertainty in lambda. Epsilon f means the relative uncertainty in f. There they are, and I've just converted them into percentages there just in case you found that easier to work in. Now because we've multiplied or divided two quantities, in this case we've multiplied them, we add together the relative, or in this case percentage, uncertainties. So the percentage uncertainty of the wave speed is 8.76%. Now I could present the uncertainty like this. I could say the wave speed is 338.8 meters per second plus or minus 8.76%. But then again, remember we want two significant figure uncertainties, so I could write it like this instead. But usually we'd want to give our uncertainty as an absolute, not as a relative or percentage uncertainty, if it's the final answer. Not always, but usually. That's what we'd be more interested in. So here's our absolute uncertainty in C. What we've done is the conversion that we had before to calculate the relative uncertainty, we've simply rearranged that, algebraically rearranged that. So the relative uncertainty multiplied by the wave speed, the mean wave speed, which is this multiplied by that, is going to give us the absolute uncertainty in wave speed, 29.7 meters per second. Notice I'm using unrounded values and rounding afterwards. Now, look at this interesting step here. I've taken my uncertainty, my absolute uncertainty, 29.7 meters per second, and I've rounded it to two significant figures, as I said we would, but I've also rounded away the decimal place. And that's important. We do want the answer to be presented to the same number of decimal places as the uncertainty. And if you're writing it in standard form, that's easy to visualize. You want the same number of decimal places. That's important. It's a convention, really. There's no point having more detail here at all when this uncertainty is 30. What's the point of the 0.8 at the end? There's no point. It's unnecessarily detailed. Okay, so just some things to remember. Just a reminder, very important, adding quantities or subtracting quantities, it's the absolute uncertainties we add. We never subtract them. Multiply or divide quantities, then we add the relative or the percentage uncertainties. We never subtract them. If you're squaring a number, you're timesing it by itself, so you just add 2 lots of that relative uncertainty. And if you're raising something to the power of 3, you add 3 lots of that relative uncertainty. In fact, if you raise any quantity to a power, to the power of n, then you multiply the relative uncertainty by n. So square roots actually make the uncertainty go down, because you halve the uncertainty, the relative uncertainty, when you've got square roots. But unfortunately, we might have really complicated formulae where we have to convert multiple times. So let's look at an example. I think I already said this bit, didn't I? This was from before. Presenting uncertainties, 2 significant figures. Yeah, I've covered that bit. So let's have a look at a more complicated example. Let's use SUVAT. So here we've got an equation, v equals u squared plus 2as, all under the square root, or all to the power of a half. And let's suppose we want to calculate v, and we are told u, a, and s with absolute uncertainties. And you can see I've picked some numbers there. Well, we can calculate the mean v pretty easily, just by taking these values and plugging them into the equation. So, instead of u, it's 10.00, we square it. Instead of a, it's negative 9.81. Instead of s, it's 1.250. Notice that I use all of the decimal places. I'm not doing any rounding when I substitute, because I need to see clearly where these data have come from. And I get my value. Okay, fine. GCSE level, that would be okay. A level, if we're given uncertainties, we better use them. So let's go ahead and use those uncertainties. Now I'm just going to push all that up into the corner because I'm going to need quite a bit of paper for this. So you might have to zoom in to see this. That's the calculation we've already done. So the first thing I'm going to do is calculate the percentage uncertainties in my quantities. So there's the percentage uncertainty in our U. And it's the usual way of doing it. Mean value divided by the absolute uncertainty divided by the mean value. And I could do the relative uncertainty in A, and I could do the relative uncertainty in S, and I've calculated those as percentage uncertainties as well. Now what we can't do is just add them all together. That would not be correct. That wouldn't be correct at all, because if you look at the equation, the U is being squared, and then it's being added to 2as, and the uncertainty in the number 2 is 0. There is no uncertainty in the number 2. We know for certain that 2 is 2. So what we're doing is we're multiplying a by s. So we could say that the percentage uncertainty in 2as is going to be the percentage uncertainty in 2, which is 0, plus the percentage uncertainty in a, which we've just calculated here, and plus the percentage uncertainty in s. So we now have the percentage uncertainty in 2as. Well, that's fine, but 2as is being added to u squared in this equation. So I'm going to have to know what the absolute uncertainty in 2as is. So we do the conversion. There's 2as, that's 2 times a times s. I haven't bothered with the negative sign because it's an uncertainty and they're always going to be plus or minus anyway. So I'm not going to bother with the negative sign. So I've just done 2 times 9.81 times 1.250 and then multiplied it by the percentage uncertainty in 2as, and there's the answer. Notice it has a unit. That is the unit of 2as. Now I'm going to want to add that to the absolute uncertainty in u squared. Well, first of all, I'm going to have to work out what the percentage uncertainty in u squared is. And that's going to be the percentage uncertainty in u plus the percentage uncertainty in u. Well, I've got the percentage uncertainty in u. I've already calculated that. That was 2.5. 2.5%. So I'm doubling it. I'm doubling 2.5%. Remember, if I've got something raised to a power, I can multiply the percentage uncertainty by that power. So I've now got 5%. I need to get that into an absolute uncertainty, so I multiply that 5% by what u squared is, which is 10.00 squared, or 100.0. So I can do that calculation, and I get 5.00 meters squared per square second. Now you'll notice the units of this absolute uncertainty are the same as the units of this absolute uncertainty. Well, that's really convenient, because I'm adding them together. Did I say percentage? Absolute uncertainty. I can't remember what I said. The units of this absolute uncertainty and the units of this absolute uncertainty are the same, which is convenient because we're adding them together. I've either just repeated myself or I've corrected where I said something wrong. I won't edit it out. I'll leave it as it is. Right, so the absolute uncertainty in u squared plus 2as, that's just the absolute uncertainty in u squared plus the absolute uncertainty in 2as. So I'll take that number there, and I take that number there, and I add them together, and I get 5.45 meters squared per square second. But u squared plus 2as is all being square rooted. It's all being raised to the power of a half. So I need to know what the percentage uncertainty is. So I get the percentage uncertainty by doing this. It's a bit of a mess. Percentage uncertainty is going to be the absolute uncertainty divided by the mean value. I just chucked all the numbers in there to calculate the mean value, and I got a percentage uncertainty of 7.22%. Now, because we're raising that percentage uncertainty to the power, we're raising that quantity to the power of a half, we halve that percentage uncertainty. To get a percentage uncertainty in u squared plus 2as all to the power of a half equal to 3.61%. Well, that's V. That's the percentage uncertainty in V. So that means that the absolute uncertainty in V is just going to be the mean value of V, which we calculated right the way back here, multiplied by that percentage uncertainty. And that gives us this value here. Okay, this is good, except we need to do some rounding, because we've got a 3 significant figure uncertainty. So we want a 2 significant figure uncertainty, and then finally we're going to round our mean value to the same number of decimal places, so that we're not not got data that's not actually useful. And that's the answer. That's what V is. Now, I'm not going to pretend that was easy. That is really, really tricky, and it needs a lot of practice. And you can get lots of practice using this QR code, scan it on the screen, go and have a look at the Isaac Physics questions. Hopefully the link still takes you to the right website, and you can have a go at doing those, and hopefully you'll do okay. And that's it. That's everything that I think you would need to know to get started. There is more, of course. We haven't looked at how to handle uncertainties on graphs. That's tying those two ideas together. There's lots of areas we haven't looked at. But these 6 areas, if you can master them before you start your A-levels, then you will find that the A-level is a much more straightforward transition. You are going to be concentrating on content first, rather than trying to catch up with the skills. So best wishes to you, and if you get stuck, you know where I am. I can help you.